Hello students, welcome to this module 9 of the segment on linear algebra in the course CHE 641 at IIT Kanpur. Okay, so in the last module we started a very important topic, namely how a matrix can be transformed to a different basis. Okay, you know that a linear operator A, if A is a linear operator, and if you express this linear operator in a given finite dimensional basis, okay, let's say the dimension of the space that you are working is n dimensional, then this linear operator takes the form of a matrix. Now the elements of the matrix of course will depend on the basis that you choose to work with. So the same operator will take different forms in different bases, right? So the detailed nature of this matrix, the numbers that form this, that constitute this matrix, will of course depend on the basis that you choose to work with. Okay, so obviously you can change the basis. You can choose to go from one basis to another, and then the matrix also will change from the detailed nature of the matrix, the contents of the matrix, the elements of the matrix of course will change from one basis to another. Now, so if I say that if you have an original basis, this is a set of original basis, let's assume the basis to be orthonormal. The original basis is EI, so a set of n orthonormal basis vectors, I going from 1 to n. Okay, now I'm going to transform from this basis to a new basis. The new basis is EI prime or EJ prime, I again going from 1 to n, right? So if I were to tell you how the new suppose since the original basis is it's an n-dimensional space, we are working with an n-dimensional space, you have n orthonormal basis vectors in the original basis. That means that each vector of the new basis can be expressed in terms of the original basis vectors. Okay, so this is like if you have n linearly independent or n orthonormal vectors, any vector A can be written as some AI EI. So each vector EJ prime of the new basis can be represented in terms of the original basis vectors, in much similar to how you represent any vector in terms of a set of orthonormal vectors. Okay, now what are the coefficients of this expansion? This coefficient of this expansion will depend on, of course, the vector J. The the basis vectors in the new basis will go from 1 to n in general, right? And of course then it is expanded in terms of all the other original basis vectors. So using orthonormality, we can say that if I take the inner product of both sides of this expression with EK, okay, now this will become I equals 1 to n Sij Ek Ei. I am assuming this to be orthonormal, so this is nothing but delta Ki. So this will become summation over I Sij delta Ki. Okay, now whenever there is a Kronecker delta over a summation, okay, the Kronecker delta will replace the sum, will kill one summation and replace this index I with the repeated index I with the index k. Okay, this is something that we have seen repeatedly. So this is nothing but S, instead of I you will have Kj is Ek Ej. Okay, Ej prime, sorry. So Skj is the expansion coefficient in this expansion. Okay, so this S is called the transformation. So Skj is the kjth element of a matrix S. Okay, this is called the transformation matrix. Okay, this is called the transformation matrix because this is the matrix that tells you how the unit vectors transform from one basis to another. This has all the details of the transformation. Now, how do we then look at suppose I take y is equal to ax in the original basis. This is just a typical linear operation, the operator A or the matrix A operating on x to give rise to y, right? So okay, just give me 1 minute. Right? So now, just as we found that the unit vectors transform like this, you can ask the question, how, suppose I express a given vector x in the original basis xi ei, I can also write this in the new basis some j xj prime ej prime. These are the coefficients of expansion in the original basis. These are the coefficients of expansion of the same vector in the new basis. You can ask the question, how are these two coefficients related? And that is very easy to understand. Let's wait for a moment to come here. So we have summation xi ei is equal to, now the same vector is represented as summation xj prime ej prime. Okay, this is j equals 1 to n, this is I equals 1 to n. Now this one, I know how ei and ej primes are related to ei primes, because we just showed how ej primes are related to ei primes. This is this relation. Okay, so I substitute that for ej prime here. So summation over j xj prime summation over I sij ei. This is nothing but summation xi ei summation over I. Okay, so I can now interchange the summations. I can say I summation over I ei of summation over j sij xj prime. On the right side, I can again write this as ei xi. Okay, so if I compare the coefficients of each of the ith unit vector or basis vector, then I will find that xi is nothing but summation over j sij xj prime, right? So if I were to write this as the vector x, the coefficients of this this is I going from 1 to n, so I can represent this as a column vector. So let's just do that. This is x1 xn. This is nothing but the matrix S dotted with x1 prime xn prime. Okay, so without loss of generality, I will write this as x is this equation, matrix equation is written as Sx is equal to S dot x prime, and similarly x prime is equal to S inverse dot x. Okay, so these are the transformation equations. If I have a original set of coefficients x, which is denoted by the column vector x, and how are they related to the new set of coefficients? Once the basis is transformed, it is related by this expression x is equal to S dot x prime, the matrix S multiplied by x prime. Okay, now let's understand how matrices transform when the basis is changed. So y is equal to ax is the expression of a linear transformation where a is the linear operator or a matrix in the original basis. Now in the new basis, instead of y, I'll have s y prime is equal to a s x prime. I pre-multiply both sides by s inverse, so I'll get s inverse a s x prime. Now you know that s inverse s is identity. Okay, so identity times y is nothing but y prime only. So this equation therefore becomes y prime is equal to s inverse a s operating on x prime. So in the original basis I had y is equal to ax. In the new basis I would expect y prime is equal to a prime x prime. Then this object here becomes, therefore, this object becomes A prime. This is the matrix A, or the linear operator A, transformed in the new basis. So you have y prime is equal to A prime x prime, where A prime is equal to S inverse A S. Okay. So just as you had y prime is equal to S inverse x prime or something is equal to S inverse x. This was a transformation rule that we just derived a few minutes ago. For vectors, then what is the transformation rule for matrices or linear operators? It is S inverse A S prime. Okay. So this is a general transformation rule. Okay. Now we are not interested in any general transformation rule. We are interested in a very specific type of transformation. Okay. What is that transformation? I am interested in that special transformation wherein A prime after transformation takes a purely diagonal form. The question is, what is that special transformation when A prime is expressed purely in its diagonal form? Okay. The answer to that is the following, which we discussed last time. I'm just quickly recapitulating the same here. If my new basis is the eigenvectors, set of eigenvectors of A, then A prime will become purely diagonal. That is, you can express the operator A in any basis, but you can also express the operator A in its own eigenbasis, that is, in a set of vectors comprised by its own eigenvectors. Then we will show that A becomes, in the transform basis, A becomes diagonal. So let's assume that the original basis is a bunch of orthonormal vectors EI, and the new basis is formed by the eigenvectors xj such that A xj is lambda j xj. Okay, this is the bunch of set of eigenvectors. Okay, now, so what is the transformation matrix? Well, the transformation matrix is very simple. Xj is nothing but summation I equals 1 to n Sij Ei, where Sij is nothing but Ek inner product xj. That is I should be Ei. So Sij is the ith component of the jth eigenvector. Okay, so this is the matrix that comprises. So if I look at this matrix will look like this. Suppose I construct a matrix comprising of eigenvectors x1, x2, xn. Okay, so you will have a matrix like this. This is x1 1, the first eigenvector second component, the first eigenvector nth component, second eigenvector first component, second eigenvector second component, second eigenvector nth component, and so on. Nth eigenvector first component, nth eigenvector nth component. So this is that matrix S. So what is this matrix S? What are the elements of this matrix S? The ijth element will comprise the ith component of the jth eigenvector. Okay, so suppose this is S. This is okay. Let me just write it like this. This is S11. This is S12. So this is the first component of the first eigenvector. This is the first component of the second eigenvector. This is the first component of the nth eigenvector, and so on. So Sij represents the ith component of the jth eigenvector. Okay, so once you realize the transformation matrix is just a comprises of the eigenvectors of the matrix A, so S, the transformation matrix, we are now expressing the matrix A in a basis comprising of its own eigenvectors. So the transformation matrix will look like this. This is the first column is the first eigenvector. Sorry, my notation is like this. The second eigenvector, and so on. Like this is what I have written down here in detail. I am just writing it in short. Sorry, this is xn. Okay. So now what is the next step? So we have realized that xsij is nothing but the ith component of the jth eigenvector. Okay. So let's now look at what is S inverse AS. Okay. So in matrix notation, this is nothing but summation over K, summation over L, S inverse of IK, AKL, SLJ. This is the ijth component of, because you know that A prime in the transformed matrix, the transform space, is S inverse AS, and S is now, what is S? S is this set of eigenvectors. Okay. So now instead of SLJ, what I am going to do is I am going to write summation over K, summation over L, S inverse of IK, AKL. Instead of SLJ, I know that Sij is the ith component of the jth eigenvector. So SLJ will be the lth component of the jth eigenvector. This is A times X. So this is nothing but summation over K. Okay. S inverse of IK. Now this is the product of a matrix and a vector, and this is an eigenvector. So this will give you simply lambda j, okay, and xj of K. Okay. Now this again is nothing but, so let me continue here. This is nothing but, so A prime is, because lambda j's are simply scalars, I can pull this out. So lambda j, S inverse of IK. Now what is xj of K? It is nothing but S of, so S of ij is xi of K, xj of I. X of jk is S kj. Okay. Now what is this? This is nothing but S inverse S. This is just an identity matrix, summation over K, lambda j, delta ij. Okay. So this is nothing but, sorry, the so this one Sik Skj, after I do the summation, becomes delta ij. So the ijth component, okay, this is the ijth component of A prime, is simply lambda ij times delta ij. What does this mean? So if I transform a matrix in its own eigenbasis, then it will become a purely diagonal matrix with the diagonal elements comprising of its n eigenvalues. Okay. So A prime is purely diagonal. This thing is called diagonalization of a matrix. This has lot of very important of a matrix. Now I have assumed that the matrix A has n linearly, or n orthogonal eigenvectors. So obviously, you know, we know which cases for which this is true. A normal matrix, of which Hermitian and unitary matrices are special cases. Normal matrices always have n orthogonal eigenvectors, so we can use that to generate this eigenbasis. So this sometimes this special basis is called the eigenbasis. Okay, because this is the basis that is formed by the eigenvectors of the matrix A. Now let's solve an example to clarify this. Okay, so let's consider a simple real symmetric matrix 2 1 1 2. Okay, so now I want to first find the eigenvalues and eigenvectors. So how do I find the eigenvalues? I have to first find this matrix. So I will do this 2 minus lambda 1 1 2 minus lambda, and I have to set determinant of A minus lambda I to be 0. That means 2 minus lambda the whole squared minus 1 is 0. Okay, so that means lambda squared minus 4 lambda plus 4 minus 1 is 0. So lambda squared minus 4 lambda plus 3 is 0. If you factorize this, you will get the two eigenvalues to be lambda 1 is equal to 1, lambda 2 is equal to 3. Okay, because the matrix is real symmetric matrix, the eigenvalues are real. So what are the eigenvectors? Again, I have to set solve this problem. A minus lambda I operating on x is 0. Okay, now I've already found what is lambda. Lambda is 1 first. So when lambda is 1, this becomes 2 minus 1 1 1 1 1. So this is a bunch of ones in the matrix. This is the first eigenvector. So this eigenvalue problems always result in a homogeneous equation. There is nothing in the right side. So x11 plus x21 is 0. The second equation also will yield the same thing. This implies that x11 is minus x21. So without loss of generality, we can set one of it to be 1. The other one will become minus 1. Okay, so this is the eigenvector x1, but it is not normalized. So I have to make sure that it is normalized in the sense that if I take this, I should get 1. So when I normalize this, what I'll do is I'll take the absolute value of this vector, which is root 2. So this is the norm of x1 is root of 1 plus 1, 1 squared plus 1 squared, it's root 2. So I divide this by root 2. This is called normalization. You can multiply by any number, but I'm normalizing it such that it has unit magnitude. Okay. Similarly, you can find that the other eigenvector, it's easy to show by substituting the second eigenvalue. You will find that this is 1 over root 2 1 1. So these are the two eigenvectors, okay, for this matrix that we started off with. Now so these eigenvectors x1 have this form, right? So let me write eigenvectors is 1 over root 2, x2 is 1 over root 2 1 1. Now the basis in which these eigenvectors are written is one of the simplest basis. So we can write this as x1 is nothing but 1 over root 2, the first vector, 1 0 plus 1 over root 2 plus minus 1 over root 2 0 1. The original basis vectors are 1 0 and 0 1. Similarly, the second eigenvector x2 can be written as 1 over root 2 1 0 plus 1 over root 2 0 1. This is the second eigenvector. Okay, this is the first eigenvector. Okay, now what I want to do is to construct I want to transform the matrix being A is equal to 2 1 1 2. I want to transform this matrix to its own eigenbasis using A is equal to S inverse A prime is equal to S inverse AS. What will be the components of S? That is it should have the eigenvectors as the columns, right? So it will have 1 over root 2 minus 1 over root 2, 1 over root 2, 1 over root 2. This is S. I can pull out 1 over root 2 and write it as 1 minus 1, 1, 1. So this will be my S. Okay. So let X prime be the vector containing the coefficients of any vector X in the eigenvector basis, and that is related to X like this. S prime, X prime is S dot X. Okay, but X is nothing but, now I want to write X, the vector X. Sorry, I wrote it the other way around. Let me take a step back. Let X be the any vector in the basis, in the original basis, the coefficients of any vector in the original basis, and let X prime be the coefficients in the eigenbasis of matrix A. So we just saw that X is equal to S X prime. So how do I write X prime? X prime, I'm going to express X prime in terms of the eigenvectors. X1 prime, the eigenvector 1 we just solved for, plus X2 prime, the eigenvector 2, right? So AX is equal to okay, so I'm going to substitute instead of I'm sorry, this is the vector, the abstract vector X expressed in terms of the eigenbasis. Okay, these are the coefficients of the vector in the two bases. So unfortunately we are sticking to the same notation. This is basically a column vector, okay, whereas this is the abstract vector expressed in different bases. So if I say what is A dot X, I'll take X here, so this X here. So I am going to multiply A dot X. It's nothing but A. X1 prime is a coefficient, so I can write X1 prime A X1 plus X2 prime A X2. But A X1 is lambda 1 X1 plus A X2 is lambda 2 X2. Okay, so I can rewrite this as A dot X is nothing but A dot X is nothing but I'm going to slightly rewrite this. X prime and lambda 1 are scalars. You can pull it around any side in this equation. So I'll first write the matrix comprising of the two eigenvectors, then lambda 1 0 0 lambda 1 operating on X1 prime X2 prime. Okay, so A dot X is nothing but, this is the matrix S, and this matrix is sometimes denoted by this capital lambda, which has just the eigenvalues in the diagonal, and then this is the coefficient of the vector X in the new basis. So this I'll call X prime. Okay, so but X prime is nothing but S inverse X. Okay, this is how the two vectors, the two sets of coefficients are related. If X is S X prime is S inverse X, right, from here. So I'm going to substitute out here S lambda S inverse X, this is AX. So this means that I can identify A to be just this. So A is S lambda S inverse, or lambda is S inverse A S. These two are interchangeable. Okay, now in this particular case, okay, so if you were to simply find Okay, if you were to find S, which we know, you to find S inverse, and then you do this operation, okay, you will find precisely that the end result after doing this is simply 1. The true eigenvalues are 0, 0, 3. So you will find that after doing all this, you find S inverse, and then you know what is A, you know what is S, we just wrote down S, right? If you do all this, you will precisely get that S inverse AS is nothing but the eigenvalue, the matrix lambda comprising capital lambda comprising only the eigenvalues along the diagonal and zeros elsewhere. This is called diagonalization. Okay, I encourage you to calculate the inverse of S. We have found what S is, right? S is this. Find S inverse, and then do this. Take the matrix A, post multiply by S, pre multiply by S inverse. You will find that the answer is purely diagonal. Okay, this is called diagonalization of a matrix. Now, closely related to diagonalization is what is called spectral resolution of a matrix. We will take the same example. It's, let's say A is 2, 1, 1, 2. So we found what the eigenvalues are. Okay. So what spectral resolution is, we saw in the last module. A can be written as a summation over I is equal to 1 to n, the eigenvalues lambda I times xi transpose. Okay, but we know what is x1. Oh, sorry, in my notation, xi transpose. Okay, we know what is x1. x1 is 1 by root 2 minus 1 by root 2, and x2 is 1 by root 2 1 by root 2 in this problem. So we have to find x1 transpose, x2 transpose. So, note that xi times xi transpose is a matrix. It's a 2 by 2 matrix in this case. So you have to take x1 transpose. So x1 transpose is nothing but if x1 is a 2 by 1 vector, that becomes a 1 by 2 vector, and x2 transpose is 1 by root 2 1 by root 2. Then I form a 2 by 2 matrix by multiplying, and then multiply by the lambda, and then sum it over. So A will become 1 times 1 over root 2 minus 1 over root 2, 1 over root 2 minus 1 over root 2 plus 3. I'm just doing the sum of the spectral resolution. 1 over root 2, 1 over root 2, 1 over root 2, 1 over root 2. If you do this, you will find that this is nothing but 1 by 2 minus 1 by 2 minus 1 by 2 1 by 2 plus 3 by 2 3 by 2 3 by 2 3 by 2. Then if you add it all up, you will get simply the original matrix 2 1 1 2. So this is called, this is a simple illustration of spectral resolution. Okay, so I just thought I'll show it using the help of examples. Now I'll again briefly revisit diagonalization and tell you about an important property of the transformation matrix. Okay, we had Ax is equal to lambda x, which is the eigenvalue problem of the matrix. Okay, and let's say there are n eigenvalues and n eigenvectors. Let's say the eigenvectors are orthogonal. Okay, these are orthogonal eigenvectors, and which can be normalized, as you know. Now let's form the matrix of eigenvectors like this. This is the transformation matrix that we spoke about, x2. Okay, so these are matrices in this sense. You arrange in each column of the matrix capital X the n eigenvectors. The first eigenvector is the first column, second eigenvector is the second column, and so on. So A times capital X is nothing but A operating on this collection of columns, column vectors. But this is nothing but ax1, ax2, this is the first column, second column, axn. I'm sorry, I'm messing up my notation a little bit. These should be superscripts. Okay, apologize for this. This is a. Okay, now because these are eigenvectors, axi is lambda I xi, so this is nothing but lambda x1, first column, lambda 1 x1, lambda 2 x2, so on, lambda n xn. Okay, so this is nothing but, so this becomes very simple. This can be rewritten as, so this is on the left side we had A operating on this collection of the matrix comprising of eigenvectors of A. So this can be written as again x times this matrix lambda, the left side, where lambda, the matrix lambda, as I told you just now, is lambda 1 0 0 0, lambda 2 0, and so on. So only eigenvalues on the diagonals and 0 everywhere. So if I multiply x inverse on both sides, I'll get this. Okay, this is something that we just saw. Now if A is Hermitian or symmetric, if A is a real matrix and it is symmetric, then A transpose is A, and then you are guaranteed n orthogonal eigenvectors if there are n distinct eigenvalues, right? Okay, such that xj transpose xi is delta ij. This is basically the inner product of xj xi is delta ij. In matrix notation, this becomes this. Okay, so if I consider this matrix X, this is nothing but x1 xn. Now if I consider X transpose, this will become x1 transpose, so on up to xn transpose. Okay, this column matrix will become all these, the first column will become the first row and so on, right? So if I consider X transpose dot X, I will get a matrix like this. So this dotted with this, x1 transpose dot x1, x1 transpose dot x2, so on, x1 transpose dot xn, x2 transpose dot x1, x2 transpose dot x2, and so on. Okay, now if you look at all these elements, these are all 0. Okay, because they are bunch of orthonormal eigenvectors. So only these coefficients in the diagonal are unity. Okay, so this will go all the way. That means that X transpose dot X is identity matrix. In other words, if I post multiply by X inverse, you will find that X transpose is X inverse. If some matrix multiplied by X is identity, that some matrix must be the inverse of the matrix X. So if X transpose is X inverse, such matrices are called orthogonal matrices. Okay, so if you transform a matrix to its own eigenbasis, what you are doing essentially is to render that original matrix purely diagonal. It's called diagonalization of a matrix, and such a transformation is also called an orthogonal transformation, because the transforming matrix, the transformation matrix, which I called S before and capital X here, capital X being because of the fact that you are specifically using the eigenvectors as the basis, such a transformation is called an orthogonal transformation. Now what is interesting about orthogonal transformation is that, you remember originally we had a set of basis vectors, okay, which are orthogonal. Whenever you have an orthogonal transformation, the angles between the vectors are preserved. Okay, if you have two vectors that are perpendicular in the original basis, they will remain perpendicular in the new basis. So this is somewhat very special about orthogonal transformations. Okay, so what is the final sort of take-home message of all this? Now, in general, diagonalization can be done very readily when you have normal matrices, because you know that normal matrices have n linearly independent eigenvectors, and more specifically, if you have Hermitian or unitary matrices, then the transformation itself becomes an orthogonal transformation. Okay, and that makes it more special because the angles between the basis vectors are preserved in such a transformation. Okay, so this has a lot of applications. Now I will point out only one application now, and I will stop this module, and I will do another application in the beginning of the next module. One application of diagonalization of matrices is if you want to solve a system of ODEs. That is, you have a system of ODEs. What does it mean? I have dt of, let's say, x1, x2, x3 is some a11, a12, a13, a21, a22, a23, a31, a32, a33 operating on x1, x2, x3. Such things are commonly encountered in process control when you linearize process model with many variables. Then you will get a set of coupled ODEs. Why is it coupled? Because typically dx1 by dt will be a11 x1 plus a12 x2 plus a13 x3, and similarly for other variables. So you cannot solve this equation independently because it is linked to the other two equations, dx2 by dt, because x2 appears here, x3 appears here, and so on. Now imagine what we can do. Suppose I say dx by dt is ax, right? Now a, I can write it as x lambda. Okay, a, I can write it as x lambda x inverse. Okay, that's what we just saw in the previous thing, right? So x inverse ax is lambda, or if I multiply this on both sides by x and x inverse, pre-multiply and post-multiply, I'll get a as x lambda x inverse. Okay, so that's what I'm writing here. So I can write it as x lambda. Now if it's an orthogonal transformation, this is also just x inverse is x transpose. Okay, I can write it as x transpose x. Okay, now let's call y as x transpose x. Let's define a new vector. So this is nothing but dx dt is x lambda. Now this is now y. Okay, now I'm going to multiply both sides by x inverse. So if y is x transpose x, then or y is x inverse x, then if I pre-multiply by okay, so let's just keep it like that, right? If I pre-multiply by x inverse on both sides, then I get d dt of x inverse x is equal to, because x is a matrix of eigenvectors, it's independent of time, I can pull it inside the time derivative. Okay, x inverse x lambda y. Now what is x inverse x? It's always identity. And what is x inverse small x? It's y. That's how we have defined, right? Therefore I can write this as d dt of y is nothing but lambda y. But what is lambda? Lambda is just purely a diagonal matrix, lambda 1 0 0. In the simple 3 by 3 case I am dealing here, it's simply like this. So in terms of the new transform variable y, our original differential equation gets transformed to lambda 1 0 0 0 lambda 2 0 0 0 lambda 3 operating on x1 x2 x3, right? Now this one, sorry, y1 y2 y3, we have transformed it. So dy1 by dt is lambda 1 y1, dy2 by dt is lambda 2 y2, dy3 by dt is lambda 3 y3. So the original set of coupled equation gets, we say, decoupled. They are decoupled because they now become separate equations. Originally we had three linked equations, right? dx2 by dt is a1 to x2, a1 to x1 plus a1 a2 to x2 and so on, right? They are all coupled. These are a set of coupled equations. Now they are decoupled. Okay, the diagonalization of this matrix makes it decoupled. So I can solve y1 is y1 0 e to the lambda 1 t and so on, and then I can transform it back to the original representation, because I know how to transform. I know, once I know y, I know how to find x, because I know that x is equal to, small x is equal to x inverse y. From here, if I pre-multiply by x, xy is equal to small x. So I simply have to multiply the answer by this matrix x, because that's how I have transformed. Then I'll be able to find what is x, right? So that's how one solves a system of coupled linear ODEs. This is true for not just third order system, it can be for any nth order system. The diagonalization of that matrix helps in decoupling the system of n ODEs, and you can find, so you can write the solution for other variables also. y3 is okay. In many branches of applied mathematics and physics, this decoupling is called the method of normal modes. For many historical reasons, which we need not go into. In mechanics, this decoupling is sometimes refers to in physics as the method of normal modes. Okay, so I'll stop here and I'll continue along similar lines in the next module with one more application of diagonalization. Okay, thank you.